Recently I've been thinking about dice, and especially how neat it is that opposite sides on a 6-sided die always add up to the same number, 7. The reason for this is easily shown. Let's line up all the numbers that are possible in a normal 6-sided die, so that 6 is matched with 1, 5 with 2, and 4 with 3. As the left column with larger numbers decreases by 1, as we go down, the right column with the smaller numbers increases by 1. So the sum between matched numbers stays the same. This is actually just a property of having an even number of consecutive numbers, which is why this generalizes to most other kinds of dice. While the cube 6-sided die, or d6, is the most common kind, when wanting to roll some number of numbers other than 6, it's typical to use the other 4 of the 5 Platonic solids. There's the 4-sided tetrahedron, the d4, the 8-sided octahedron, the d8, the 12-sided dodecahedron, the d12, and the 20-sided icosahedron, the d20. Actually, Platonic solids are really cool in the ways that make them perfect for fair dice. Fair meaning that each face has an equal chance of being rolled. Platonic solids are defined as convex, meaning that they bulge outward instead of awkwardly inward. In other words, the angles between adjacent faces are always less than 180. They're three-dimensional objects, and they're regular polyhedra, meaning each face is congruent and a regular polygon, which in of itself means their angles and side lengths are also congruent. The most important feature of Platonic solids in our case is that they're particularly symmetric, meaning that there are a lot of ways to rotate and reflect them, which leave them invariant, i.e. identical to what they were before the transformation. These are identified by their symmetry groups, which include exactly what combination of reflections and rotations exist for each solid. These are the tetrahedral, the T group, the octahedral, the O group, which is the same for the cube, the icosahedral, the I group, which is the same for the dodecahedron. Relatedly, each vertex, edge, or face on a Platonic solid is identical. This means that they are also equidistant from the solid center, and thus makes them like approximations for spheres, which is cool. These polyhedra are also actually very famous in the history of geometry. They're named after Plato, who admired mathematics and thought that it played an important role in nature. He associated the Platonic solids with the 4 classical elements, earth, air, fire, and water, via geometric properties, like fire being the tetrahedron because it was sharp and it hurt, it was the pointiest, and water being the icosahedron because it was like a ball and it rolled or flowed in one's hand. And in fact, due to their symmetric properties, their structure is seen in nature, such as determining the shapes of molecules. Seeing as electrons want to be as far away from each other as possible, distributing them on sphere-like shapes makes sense. The ancient mathematician Euclid proved that these 5 were only possible Platonic solids as such. First, each vertex of the solid should be a vertex for at least 3 sides, because if it were 2, it can enclose a 3D object. Second, the total angle among the 3 or more adjacent sides must be less than 360 degrees, because if it were equal to, then the vertex would be a side, and if it were greater than 360, the shape would be concave. Third, since regular polygons with 6 or more sides must have angles of 120 or more, there cannot be 3 or more of them at a vertex. Thus only triangles, squares, and pentagons can be the common shapes for the faces. For triangular faces, there can be either 3, 4, or 5 at a vertex, resulting in the tetrahedron, the octahedron, and the icosahedron respectively. For squared faces, only an arrangement with 3 squares at a vertex is possible, resulting in the cube. And for pentagonal faces, again only an arrangement with 3 pentagons at a vertex is possible, resulting in the dodecahedron. These are the 5 Platonic solids. There is one more common and prettier proof that comes about as a result of work on the Euler characteristic, and the observation that V minus E plus F is equal to 2 for convex polyhedra, which includes the Platonic solids, where V is the number of vertices of a solid, E the number of edges, and F the number of faces. If we say that the number of sides of each common face is n, then if we count up all of the sides of all the faces, we get n times f. Since each edge is bounded by 2 faces, we get that n times f is equal to 2 times e. Further, if the number of edges which meet at a vertex is r, and since each edge connects 2 vertices, then we get that r times v is equal to 2 times e. Plugging these 2 equations into the first equality, we arrive at 2e over r minus e plus 2e over n is equal to 2. And by dividing by 2e, we get that 1 over n plus 1 over r is equal to 1 over 2 plus 1 over e. We know that n is 3 or more as the polygon with the least sides is the triangle, and that r is 3 or more, as I explained earlier, since at least 3 faces must meet at a given vertex. N and r can't simultaneously be greater than 3, since that would make the left-hand side of the equation less than or equal to 1/2, which would be impossible for a finite number of edges. It's then easy to find the 5 different cases or values for n and r. These are 3 and 3, 4 and 3, 3 and 4, 5 and 3, and 3 and 5, respectively. The tetrahedron, whose sides are triangles, 3 of which meet at a vertex, it has, by the equation, 6 edges, 4 faces, and 4 vertices. The cube, whose sides are squares, 3 of which meet at a vertex, it has 12 edges, 6 faces, and 8 vertices. The octahedron, whose sides are triangles, 4 of which meet at a vertex, it has 12 edges, 8 faces, and 6 vertices. The dodecahedron, whose sides are pentagons, 3 of which meet at a vertex, it has 30 edges, 12 faces, and 20 vertices. And finally, the icosahedron, whose sides are triangles, 5 of which meet at a vertex. It has 30 edges, 20 faces, and 12 vertices. Also, notice the symmetry between the cube and the octahedron, and the dodecahedron and the icosahedron, and how that relates to the symmetry groups. Platonic tangents aside, back to the dice. As I mentioned earlier, dice tend to have the property where opposite sides add up to the same number, except for the tetrahedron, which has no opposite sides, that is, no reflective symmetry parallel to one of its sides, which anyhow is equal to the number of sides of the dice plus 1 when following the logic from before. Now, finding variations of these for the different kinds of dice isn't hard at all. Since each pair of numbers on opposite sides are independent of one another, it's easy to construct. However, something a little harder is to construct dice where, by looking at it from any orientation, the divisible sides always add up to the same number. To be specific, the orientations where half of the possible sides, or the largest number of possible sides, are visible. First, let's eliminate the tetrahedron, because it's possible to have a combination of literally all sides with each other, such as one orientation on 1, 2, and 3, and another on the same die with 2, 3, and 4, obviously equaling different sums. Then let's look at the cube. First, we know the total sum of all the sides is 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is equal to 21. Then let's imagine two orientations opposite one another, that is, with opposite vertices at their center. If we assume one orientation which these 3 numbers adds up to some value x, and that we found the nice symmetric dice we were looking for, then the other orientation with the 3 other numbers must add up to x as well. Together, these 6 values must add up to 21 and to 2x, so we get x is equal to 10.5, which is not a whole number, and thus no symmetric 6-sided die exists. The same trick, however, doesn't eliminate the other Platonic solids, so let's continue. Next, the octahedron. The sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 is equal to 36. Using similar reasoning, where opposite orientations show equal sums of x, where 2x is equal to 36, gives a sum of x is equal to 18. So it might be possible to create my very symmetric 8-sided die. So how do we find these possible dice? When solving problems in mathematics, or really anything, it's helpful to simplify down solving it to a process of solving easier or different but equivalent problems. So let's start with trying to find all the different possible sums of 4 unique or different numbers from 1 to 8, which add up to 18. These sums would then constitute all the different possible combinations of numbers seen from particular orientations of the die. To do this, let's simplify it down further and make a list of all the possible sums of 2 numbers in our range. The lowest possible sum of 2 of the numbers from 1 to 8 is 3, which is 1 plus 2. Next, 1 plus 3 results in 4. Both 1 plus 4 and 2 plus 3 give 5, and so on, until 7 plus 8, which gives 15. Now let's look at these largest sums and find the combinations of 2 of which sum to 18, which we'll call corresponding sums, such as with 3 plus 15, 4 plus 14, 5 plus 13, and so on. If we then, for all of these combinations, make a list of all the possible combinations between corresponding sums, then we will have found all sums of 4 numbers in our range 1 to 8, which equal 18. Some examples. Let's start by looking at 3 and 15. The only possible combination is 1 plus 2 and 7 plus 8, or in all, 1 plus 2 plus 7 plus 8 is equal to 18. Next, how about 5 and 13? We can combine 1 and 4 and 2 and 3 with 5 plus 8 and 6 plus 7, which gives the 4 different combinations: 1 plus 4 plus 5 plus 8, 1 plus 4 plus 6 plus 7, 2 plus 3 plus 5 plus 8, and 2 plus 3 plus 6 plus 7. All in all, we get 8 and only 8 different 4-number sums shown on the screen. I've grouped these in pairs, where each sum in a pair utilizes all the different numbers. That way, if you see one of the sums in a particular orientation of the die, you know that the opposite orientation shows the other sum it's paired with. Now remember how earlier I said that the octahedral symmetry group was the same as for the cube. That can be seen when you remember that the cube has the same number of vertices as the octahedron has faces, and vice versa. I use this fact when I replace our octahedral die with this cube wireframe, where the numbers previously on the face of the die are now the vertices. Doing this, each possible orientation showing our sums is a face on this cube. This makes our next part much easier. Let's take a random one of the sums, say 1 plus 4 plus 6 plus 7, and arrange the numbers on the top face as such. It should be pretty obvious that we can arrange the other 4 numbers below to create one of our perfect dice, so that each vertical edge has 2 numbers which add up to 9. In this case, 8 is below 1, 5 is below 4, 2 is below 7, and 3 is below 6. This way, the top face and the bottom face add up to 18 each. And since each side face is equal to the sum of the 2 unconnected vertical edges, they must equal 9 plus 9, or 18. I'll say this is the first of our possible perfect octahedral dice, which I count as the same as any rotated or reflected variants shown on the screen. Really, the most defining aspect of it is which 2 of the 8 possible sums it lacks. In this case, 1 plus 4 plus 5 plus 8, and its opposite 2 plus 3 plus 6 plus 7. To generate the other dice, all we need to do is jumble up the ordering of the top faces numbers in a way not possible through reflections or rotations. So in this case, I'll switch the 4 and the 7, and therefore the bottom 5 and 2 as well. This gives our second die, which now lacks the sums 1 plus 2 plus 7 plus 8, and its opposite 3 plus 4 plus 6 plus 7. Our third die, which switches the 4 and its corresponding 5, with the 6 and its corresponding 3, now lacks 1 plus 3 plus 6 plus 8, and 2 plus 4 plus 5 plus 7. Now we have 3 of our nice dice, which lack 3 pairs of sums out of the possible 4 pairs. One could guess then that there's a fourth die which lacks the remaining sum 1 plus 4 plus 6 plus 7, and its opposite 2 plus 3 plus 5 plus 8. Well, finding that is a little bit harder. To solve this, I'll go through a couple of possible cases for this die, arbitrarily depending on where the 1 and 8 are situated. First, let's look at all the possibilities where 1 and 8 are next to one another, that is, vertices on the same edge. There are 3 possible sums which include both the 1 and the 8, and add up to 18, that is, with 2 plus 7, 3 plus 6, and 4 plus 5. However, the edge consisting of the 1 and the 8 is only part of 2 faces, or 2 sums. Therefore, this particular die must lack one of the aforementioned sums, which include 1 and 8, and further can't not have the sums that it needs to lack in order to make our fourth die. So alright, the second case. What are the die possibilities where the 8 and the 1 are separated by just one vertex? That is, they aren't on the same edge, but are now on the same face. This one's a little bit easier. Using similar logic as before, now only one sum including 1 and 8 is possible, as there's only one face which includes them both. We need all 3 on our dice. Furthermore, in case 3, where 1 and 8 are opposite one another, not a single one of the 3 possible 1 and 8 sums are possible. Finally, there we have our 3 possible, perfectly nice octahedral dice. My script at this point exceeds what I've originally planned to write by about 2,000 words, so I'll leave figuring out the dodecahedron and the icosahedron to you, the viewer. So as always, thanks for watching, and tune in for next time.